Hey, man.
Oh, yeah, first one.
What happened on that test, dude?
I have no idea.
It's atypical of you to get such a score.
I know.
And the stuff you attached for the answers wasn't even like related to the question, and so it's kind of weird. So maybe visit me in TSS.
Okay. Is there like a cutoff date I can get assignments in, or did it already pass?
Or you can still turn assignments in, or you just get late credit. All right. So I guess the missing people didn't get the memo about the Zoom link, huh? You guys get like pop-ups on your phone that tell you that I updated something or that I posted that? Is that how you guys find out, or how does that work? You look at your email? We just see Google Classroom. But I mean, does it pop up on your phone? I got Google Classroom on my phone, so stuff pops up there in my notifications. I'm assuming you guys would do that too, no? Well, what, you have to like log into Google, you have to click on Google Classroom to see it, or do you get another notification on email or someplace? You have to turn it on the app. Well, yeah, turn it on then, geez. All right, we actually have just about everybody in. We're just, oh no, we're missing Elena. Is Elena in here? Did I just miss you coming in? Okay, so we're missing Elena, missing Olivia, and we're missing Ryan. Ryan, are you in? All right, so no Elena, no Ryan. Okay, well, hopefully, I can't open two Zooms at the same time, so I can't go in the old one and like check to see if they're in there. Maybe I can, I don't know. Phone and email notifications, 3 people's Google Classroom notifications. Well, I hope I'm one of them. I hope you don't have lesser teachers notifying you and not me. Anyway, righty, test. The test. I forgot what I did with you last time about test analysis. I know I want you to get together in a group again and talk about the questions. I just forgot how we set it up. Did I assign you in a group, or did I just let you pick them? I don't remember anything.
You assigned us.
Okay, well, I didn't do that this time because I just didn't have any time. I did not have time to do that. I'm sorry that I didn't assign you, but I still want you to do a test analysis. So in years past, I've always just had kids do that on their own. They find their own group of people. They work with whoever they want to work with. All I ask is that I don't want like 4 people that failed the test together And I don't want 4 people that got A's on the test together, because that's kind of useless then. In either direction, that's useless. If we had a nice mixture of people who didn't maybe do so well and then somebody else who did pretty well, then, you know, people can help each other and people can benefit. Half of us were in a random one because nobody got together. Okay, all right. Well, I think once again that you can see your tests by going back to the assignment and then clicking on a thing, and then you can see your answers or something. And then you can, like, in that group, you got to make your own Zoom with the people and get together in Zoom, and you guys can make your own Zoom meeting, right? You can just sign up for your own Zoom account if you want to, or I don't know, maybe there's like a school one that you can do. I don't even know if you guys have a school Zoom accounts, who knows? But anyway, the point is you can make your own Zoom account and start a Zoom meeting and invite your friends in there, and then you can talk about the test. Now, this is kind of tough for me to have accountability. Like, I can say, I want you guys to do this, and you guys are all like, oh yeah, we're going to do it. And then people don't do it. You just kind of like, oh yeah, sure, we did it. You know, like, I don't know. So we could do a little accountability thing where we, I know nobody's doing needlepoint during my class, right? Because that would be really like a giant insult to my ego. That my voice is so boring that I got to do needlepoint or something. List all the things that are more fun than Volk's class. Well, needlepoint. Arranging the sock drawer is more fun. Folding laundry is more fun. Emptying the dishwasher is more fun. Picking up the dog poop in the yard is more fun. Yeah, let's make the list, okay? And then send it to me to boost my self-esteem. So thank you for that. Anyway, what am I talking about? Oh yeah, accountability. So here's an idea. When you're in your little Zoom meeting with your group of people, and drinking, what? I don't even know what that means. Okay, I think we just lost it. When you're in a little Zoom meeting, and I don't care, I mean, you could have 8 people in there, I don't care, whatever. You just talk about it, everybody says something, everybody contributes. Whether it's you asking a question, whether you're whatever. Anyway, yeah. And then you go to Screencastify and you record your meeting. You record the screen of all the people in there, all the cameras on, listen to everybody talking, and then you submit that video to me, and it's evidence that you guys work together. Brilliant. Brilliant idea, Volk. Just genius. Okay, so that's a thing. The yum comment reminded me of a thing that happened many years ago. My whole family had dentist appointments all at the same time, you know, for teeth cleaning. We used to go downtown for a dentist down there, and we in this tall building downtown Milwaukee, and we had, I don't care, it could be 3 people, it could be 9 people, it could be whatever. So it's just one of those tall buildings in Milwaukee that had like 30 floors or whatever, or 20 floors. We had to take the elevator, and we're all coming out of the dentist, and I guess we saw somebody we knew or whatever it was, but somebody in the elevator said, oh, what did you have done? And somebody said, oh, I had to have a tooth pulled. And my wife, like being socially awkward, said, yum. Like her response to the, oh, I had to have a tooth pulled, she goes, yum. Like she didn't, like it just slipped. You know how like you say stuff and you don't want to like say it? Like that's not what you meant to say, but that's what came out of her mouth. That was like, I don't know, 16 years ago. So we still make fun of her to this day. Like when somebody says something really weird or whatever, we say yum, because just to make fun of her, and she gets mad. We spent one day on water tension. It's not freaking called water tension, it's called surface tension. My God, did you learn nothing? Oh my God. This is the reason I cry at night. Dentist diaries, yeah. Anyway, so that was a heartwarming story from my life. So I hope you wrote that down. There'll be a question on it. Everybody clear? Get together with some people. If you need help being assigned into a group, like let's say you don't know most of the people in here, or you don't like anybody here or whatever, tell me, and then I'll figure out a way to get you in a group. I'll arrange groups or whatever. But right now I don't want to spend any more class time on that. Speaking of groups, and something that I forgot to mention the last couple of times, I asked you guys to make your own groups for the for the signal transduction Jamboard, and that was assigned, that was explained. Everything was crystal clear, blah, blah, blah. And then I kind of forgot to mention it again, but I'm still expecting you guys, I expected you guys to have that done. And many of you guys actually did it, and you did a nice job. And then some of you didn't. Some of you just kind of like, oh, well, he's not mentioning it again, so therefore it goes away. Therefore it doesn't exist anymore. That's not how that works. Once I mention it and I assign it and it's due on Google Classroom, I don't have to bring it up every time because my brain is like on, you know, my friggin' brain is on like CDK and MPF and all of this stuff. And today it's going to be on glycolysis and Krebs cycle and stuff like that. So I'm in the zone of, you know, glyceraldehyde 3-phosphate, so that I'm not thinking about something I assigned last week. And I'm still assuming you guys are not just going to ignore it because I didn't remind you every single time. Right? Those sound like illegal drugs? No, I don't tell you about my illegal drugs. That would get me in trouble. I keep those in the trunk of my car. So wait, am I recording this? Oh my God. I gotta edit that out. Dang it. I mean, legal. I said legal, I meant. Yes. All legal. Any things we need to talk about? Okay, I don't have the test entered in Infinite Campus yet. I don't have time, and I still have to figure out what grades are going to be what grades. But if you're wondering if you passed or not, it's going to be something in the 30 to 31-ish range is passing. 31 out of 52-ish is going to be the passing, like the D, you know, or whatever the cutoff is, minimal or whatever fake grades we got. And then I don't know, figure like 90 and up is like your E, your excellent, 90% ish. So whatever that ends up being, 90% of 52. So I don't know, 36 or something, 35, whatever. Is there a curve? Well, that's already built in. I'm already being pretty, yeah, I mean, I build a curve in because, although I shouldn't because it's virtual and you're using notes and like you should all be getting A's on this. Like people still, like I'm letting you use notes and I'm asking you to draw a mechanism that I give you the notes for in class and then people still screw it up. Like, how? Anybody that got below passing, well, okay. Anybody got below passing, you come to TSS tonight and we'll chat. Come TSS after class today. If you can't today, then come on Tuesday. You talk to me at TSS. So if you got below like 31 or whatever it is, whatever the number is that I'm going to figure out, I'll hopefully punch these in the next couple of days. Then you visit me in TSS and we'll figure something out. Okay. Any issues, questions, comments, compliments to me? You know, no compliment, no compliments. Thank you.
Your class is really nice. I just need something to do with my hands.
Oh, okay. That was a nice compliment, even though then you still did needlepoint. I'll accept it. And it sounds like the link worked, Claire. You're in, so no issues today, right? Awesome. That's really good news. Well, we're both crying together at night, so that's great. Everybody's crying, and you know, the hive cry. Criminal Minds Group. Yeah, I don't care. The chat is the chat is disintegrating again, like usual, just like every single time we have class. So I'm going to shut it off. All right, let's start with we're going to cover chapter. I think it's chapter 9 and 10. It's, well, whatever the numbers are of the chapter. It's respiration for one of them, and it's photosynthesis. That's it. All we have is 2 chapters in this unit. We have respiration and photosynthesis. So it's nice. Only 2 chapters to worry about instead of like those units where there's 4 or 5 chapters. So that's kind of cool. I'm going to try to zip through it pretty quickly. A bunch of it will be a review from freshman year, but there obviously also is going to be new stuff, you know, a little bit more advanced stuff. But overall, shouldn't be too bad. I hope you guys do all right with this. But I will go pretty fast, and I'm going to record it, and I'm going to post it, and you can always watch the video again, and I'm going to post lots of resources. There's lots of stuff on my Google Drive. I already posted stuff on Google Classroom. I posted the PowerPoint, so you guys can go and open that now. I posted the reading guide, and then I don't know, some other stuff.
Is this reading guide gonna be optional or is it
Nope,
mandatory?
this one's required. It's only going to be 2 for this unit, so we're just going to do the. Yeah, I read your comment, Cadence, but that's kind of like individual issues that we can talk about one-on-one, not like in front of the whole class. All right. So, and it's something you can discuss in your group. You can discuss that in your test analysis group, and you can talk about the questions and see, hey, who got full credit and stuff. And by the way, on that last question where you guys got to pick your topic, that's the one where most people lost points on that one, where you got to pick your own topic. That's where people lost them. It's like, for crying out loud, you got to pick it. Oh, you ran out of time. Okay, running out of time, I guess, would be the explanation. But like, if you got to pick it, it should be the one you know the best. And then like people still screwed it up after you picked your, like, that's the one you knew the best, like really? So that was kind of weird. Anyway, and by the way, like, I didn't just want you to write like this much for a 10-point question. Like, obviously you write everything you know. And if this is all you know, well, that's why you didn't get a 10. So basically that's how that works. Only a few people got 10 out of 10 on that last one. Most people lost something. Okay, so we're going to start with chapter 9, which is respiration. We're going to start with some stuff that'll be a little bit foreign to you. I'm going to talk about oxidation and reduction reactions, which you haven't even learned in chem yet. And the seniors will know this. The seniors know this from like AP Chem and stuff like that. The sophomores aren't going to know it, but it's okay. We're going to do like a quick and dirty version of it. That's going to be pretty easy. And then we'll talk a little bit about NADH and NAD plus and its role. And then we'll probably dive into glycolysis right away. Okay. So, and by the way, all the people that are still whining in the chat about running out of time, the reason you're running out of time is because you didn't learn the material well enough and you had to use your notes way too much. Because I made these tests shorter than the tests last year. They're shorter, and I'm giving you more time than the kids had last year, and you guys are still running out of time. And that's because they didn't get to use notes. So here you're paging through notes and notes and notes and this, and can't find this and can't find that, and who knows what you're doing, and that's why it's taking so long. All righty. Okay. Everybody by now has that PowerPoint downloaded, but you can just follow along right now on mine because I'll pop the stuff up on the screen so you don't have to try to do like dual screen or anything like that. You want to have your notebook out though, because you might want to add things or write things down. All right, so let's check it out. Okay, so I am pretty sure I talked to you guys about anabolic and catabolic pathways, but if I didn't, one of my analogies is that catabolic reminds me of cat, and cats destroy things. Cats like break things, they knock stuff off the counter and it shatters. So catabolic is destructive. It breaks large molecules down to small ones and it releases energy, okay? Anabolic is building up like photosynthesis, for example, and that's what we're going to talk about in chapter 10 then, but right now we're on chapter 9. So we're just going to talk about catabolic right now. So anabolic builds up, catabolic breaks down. The pathways of respiration, in other words, the process of us eating food, breathing oxygen, and then breaking down that food and making ATP, those pathways are similar to burning. They're similar to burning or combustion, you know, of fuel. Glucose that we eat is like fuel. It's like gasoline or coal or whatever, and we break it down into CO2 and H2O, and that's kind of what happens when we burn things. The difference is, though, that when I'm burning a bunch of stuff, like if I'm burning a bunch of wood, or I could even burn sugar, like we could use the same stuff as we use in, you know, for our food. I can take sugar and burn sugar. If I burn the sugar, all of the energy of the sugar is released as heat. And it's all wasted. It goes into the universe. We call that entropy disorder or whatever, and it's all gone. That's not gone, but it's distributed sort of evenly, and it's no longer useful. So the energy isn't destroyed or anything like that. It's conserved, but it's no longer in a useful form. It was all kind of wasted, in other words. But with catabolic pathways, when we break glucose down gradually, step by step, like in the process called glycolysis, glyco, sugar, lysis, splitting, we can harvest some of the energy. We can grab some of the energy that would normally just be released as heat and lost, but now we can grab it and use it for something useful. You can use it to do things in the cell, like we can use it to pump sodium out. We can use it to contract muscles. We can use it to bend flagella back and forth, or to move vesicles, with my kinesin motor molecule, or whatever it might be. Lots and lots and lots of different functions that we can do with that energy. And the energy, obviously, is going to be eventually put into ATP. But to get it there, we need sort of a carrier molecule. We need a shuttle. We need something that takes the energy and brings it to ATP eventually. And the way that works is our cells use something that's called NAD+. It stands for nicotinamide adenine dinucleotide, which really is neither here nor there. You don't really need to, you could learn that because you want to, learn and because you want to be smart and stuff, but NAD or NAD+ is perfectly fine. Perfectly fine way to phrase it. All right, there's a couple of more terms that we should talk about, and that's oxidation and reduction, or oxidation reduction reactions. They call that in chemistry redox reactions. The re stands for reduction, the ox stands for oxidation. An oxidation is taking electrons away from a molecule. Okay, and generally when that happens is we're taking energy away from the molecule. So as those electrons are getting stripped away from the molecule, it's also releasing energy along with those electrons. That's an oxidation. The only reason they call it oxidation because the atom that's really, really good at taking electrons away is, guess which element? Rhymes with schmoxygen. Go ahead.
Oxygen.
Oxygen, exactly. So that's why it's called oxidation. Okay, it's kind of a stupid name for it because it doesn't have to be oxygen that's oxidizing things. It could be other molecules. It could be other, particles or whatever. It doesn't have to be oxygen, but that's what it's called. So, all right. Reduction is getting electrons. So the molecule that gets reduced is getting the electrons and it's getting energized in the process. So it's building up energy. All right, so that's also confusing because reduced sounds like less. Like if I'm getting reduced, I'm like shorter, or if I'm smaller, or whatever it is, I'm losing something, when actually I'm gaining electrons. So the reason why it's called that is because it's a reduction of charge. The charge is going more negative because you're getting electrons. That's what they're talking about, the reduction. But reduction is getting the electrons and generally getting energized most of the time in the way that we're going to talk about it all the time. And an oxidation is losing those electrons and losing the energy, giving it to another molecule. An oxidation agent is exactly the opposite then. An oxidation agent is one that takes away electrons from another molecule. So the oxidation agent gets reduced. That's confusing sometimes to kids. The oxidation agent, like oxygen, gets reduced because it's oxidizing the other molecule. So I should probably write this down up here. Oxidation is getting electrons taken away. And here I'll put receiving electrons. Can I abbreviate electrons E-? Are we that smart now? Yeah, we're that smart, we can handle it. So the oxidation agent gets reduced, and the reducing agent is one that gives electrons to, it's reducing something else, it's giving the electrons to something. So it gets, okay, tell me, you tell me now, it gets
Oxidized.
oxidized. It gets oxidized. All right, and it's giving that energy to another molecule then. And that's what's happening in these catabolic pathways in respiration, whether it's glycolysis, whether it's the Krebs cycle or the citric acid cycle, or whether it's the electron transport chain. We're passing electrons from one molecule to another and sort of saving that energy that way and holding on to that energy and using it for something practical, for something useful, versus just losing it all as heat. Anyway, so NAD plus, like I said, has a big role in that. And then obviously ATP is the final molecule that gets the energy that then is able to use it for something practical, something useful in the cell. All right, let's talk about bonds a little bit. So there's different kind of bonds we can talk about. We can talk about non-polar bonds, non-polar covalent bonds, and we can talk about polar covalent bonds. And the reason these are polar is why? What do you see in there that right away you know it's going to be polar? What's the clue? Oxygen is the clue. Yeah, oxygen is super electronegative. It pulls the electrons to it. So what happens is if you have like a CO connection, what happens is the oxygen pulls most of the electrons to it, and there's very few electrons at the carbon. So electrons spend a whole lot of time by the oxygen like this, and only a little bit of time by the carbon. That makes the oxygen slightly negative, and it makes the carbon slightly positive. Whether that's a double bond or a single bond doesn't really matter. Hydrogen and carbon are about the same electronegativity. They're about equal. So a carbon-hydrogen bond, the electrons are going to be sort of equally distributed between the two. There's this like cloud that is kind of the same all the way between the two where it's not uneven at all. All right, so the way you can look at this, you can kind of look at it like this. I don't know if this is going to make sense or not, but I'm going to try it anyway. Let's say we have carbon and hydrogen. The electrons are kind of like in the middle, so they're like up here. Okay, and if they're going to fall in one direction or another, they're going to fall down. In other words, they have a lot of energy up here because they're on top of a hill. With oxygen and carbon, for example, what's happening is this. Let me draw it like this. The electrons are all down here at the bottom of the hill. Okay, they've already fallen down to the oxygen. They're at the bottom of the hill. So when your sled is at the bottom of the hill, does it have a lot of energy or low energy? Low energy. So if your bike's at the bottom of the hill, is low energy. If your bike or the sled is at the top of the hill, that's high energy. So the way you can visualize it is that the electrons that are between carbon and hydrogen, they're like on the top of the hill, they have a lot of energy. They can still fall down towards oxygen. And as they fall towards oxygen, they can release that energy. All right, so a bond between carbon and oxygen is low energy. A bond between carbon and hydrogen, or a bond between carbon and carbon, or a bond between hydrogen and hydrogen, any of the nonpolar ones, is high energy. Now, chemistry people are going to tell you that bonds don't hold energy. Well, it's a bunch of semantics. It's a way you phrase it, and it's really not worth arguing about. I can tell you that this compound, these compounds on the left have a tremendous amount of energy, and these compounds that that don't have these kind of bonds don't have a lot of energy. That's really what the point of this is. So I'll give you an example. So this compound here, let's look at this one. This compound. Oh, it's right here. This guy looks like this. Would you say those 4 covalent bonds between carbon and hydrogen give that compound a lot of energy or low energy? This is methane, by the way. Are they the left or are they the right? Are they polar or are they, sorry, are they non-polar or are they polar?
Non-polar.
Yeah, they're non-polar. So high energy or low energy?
Hi.
High energy. What do you know about methane? What can it do? If you put a match to methane?
Lit a fire.
Yeah, it's going to burn. It's going to explode. It's a huge amount of energy. We use it as fuel. We use it as fuel. We use it to heat our house. It's natural gas. Okay, so versus, let's say, this molecule. Try using that as a fuel. Put this in your car. See how that goes. Okay, all the electrons already fell down towards oxygen. They're all down here already. It's fighting me. So all the electrons are closer to oxygen. They've all fallen down the hill already. They're low energy. So try using water as a fuel. It doesn't work. Water doesn't hold a lot of energy in it. Oh, but they can use water to make hydrogen and then it's a fuel. Yeah, you have to put energy in to make water into hydrogen, okay, to hydrogen gas or whatever. You have to apply electricity. It costs a ton of energy to do that. That's not free. because the energy in this molecule is very, very low, and the energy in this molecule is very, very high. And it's because of the way these electrons are distributed between the atoms. Is everybody clear on that so far? This is the reason why fats have a huge amount of energy, because fats are mostly carbon-hydrogen bonds. Tons of energy. This is why carbohydrates have a pretty good amount of energy, not as much as fats. And that's because carbohydrates have some, so look at this guy here, glucose. They got some oxygens, okay? Well, if there's some oxygen in there, there's already some areas, some bonds that are lower energy, but most of them are carbon-carbon, carbon-hydrogen, so those are tons of energy. So glucose has quite a bit of energy, not as much as fat. So the question here asks, which of these contains more high energy bonds, molecule 1 or molecule 2? Which one has more energy? Well, basically what we're looking for is the one that has less oxygen.
2.
2 is exactly right, and 2 is a fat, it's a fatty acid. So we know fat has more calories than sugar, you know this, right? Carbohydrates have less calories than fat by gram, by mass. It's because fat has more energy in it because of all those carbon-hydrogen, carbon-carbon bonds. This slide does not look nice. I might have to delete some of this before I post this. This is ugly. It's ugly. Glucose is a lot of energy bonds. We already talked about that. Okay, how is this released during respiration, and what is the role of NAD+? NAD+ oxidizes food molecules by removing 2 electrons and 2 hydrogens. So it strips away electrons, takes them into itself, and it forms NADH. NAD+ is low energy. NADH is high energy. Okay, it has now gained those electrons. There's 2 electrons. One of them neutralizes this positive on the NAD. The other one neutralizes an H+. Okay, so this H+ that sticks itself on there also gets an electron stuck to it. So there's 2 electrons added to this molecule to make NADH. And this thing is high energy. This can now do a bunch of things in the cell. As a matter of fact, it is the molecule that's going to help us get lots and lots of ATP in mitochondria. So all your life, you've been saying, the mitochondria is the powerhouse of the cell. Well, today you're going to learn a little bit more about it and how do the mitochondria actually make ATP? Why are they the powerhouse of the cell? And the answer is they will use NADH and use some trickery to get ATP for the rest of the cell and for, your body. All right. Oh, this is supposed to be carbon dioxide. I was just too lazy to put the 2 oxygens on, but it shows you that this is low energy. That's a low energy bond here, obviously. All right. Any questions on this? So if NAD and NADH is new to you, just think of it as like an in-between. You got food over here with a bunch of energy. On the other end, you got ATP. We got to get from the food to the ATP. NAD+ is able to carry that energy from the food to ATP. All right, not directly, but through some trickery, which we'll learn about in this chapter. All right, was there a question? Check the chat. We're going to okay. All right. So respiration or cellular respiration. So first of all, I don't want you to think about like, oh, respiration is all about the lungs. We're going to learn about the lungs and the alveoli and all that stuff and the bronchi and no. Yes, the lungs are important. The lungs provide us with oxygen, and we're going to learn why we need oxygen. Why is oxygen so important? What's the point of it? We'll learn about that in this unit, in this chapter. But cellular respiration, so basically breaking down food, and with the end goal of making ATP, has 3 main parts. 3 main parts. Glycolysis is the first one. The Krebs cycle, or a lot of people now, it's very trendy to call it the citric acid cycle. I'm not that big a fan of the citric acid cycle, but I like calling it the Krebs cycle because it's named after Hans Krebs, the German scientist that worked on that and figured some of that stuff out. And then the third part is the electron transport chain, or ETC. And then there's some fancy terminology that we'll go over. I'll explain that to you once we cover the ETC. And 2 of those parts take place in mitochondria. The only part that doesn't is glycolysis. That takes place in the cytoplasm. The rest of it, Krebs cycle and electron transport chain, takes place in mitochondria. And we'll take a look at where in the mitochondria, what parts, and what exactly goes on there, because I know you're dying to know, like, what are all these steps? We must learn them. I can't live without knowing about NADH dehydrogenase. I must know, Mr. Volk. I know that's how you're feeling right now, and I will show you all that stuff. Isn't oxygen important because the only resin we need it is for the electron transport chain? That is exactly right. We need it for the electron transport chain to keep those electrons moving. Without oxygen, we wouldn't be able to do that, and everything would come to a grinding halt and we would die. All right, here's some new stuff that you haven't learned about before. The concept of oxidative phosphorylation versus substrate level phosphorylation sounds really, really complicated. It sounds complicated. It's not that complicated. It's not so bad. All right. How am I going to say this gently? My PowerPoint and my notes that I give you are incomplete. I have keywords up here. You're gonna at some point have to write things down. Okay, so I'm hoping that people are writing some of this down. So I'm just saying, okay? And if I'm going, thank you, Noah. And if I'm going too fast, then just tell me to explain it again. Just shout into the mic and I'll go over it again. I'd be so happy to hear from you. I wouldn't even make fun of you hardly, unless it's Noah. But anybody else, I would be sort of nice, maybe.
Can we go over it again?
Don't do it. Don't do it for Snim. Don't do it for Snim.
Everything? Like in the beginning? Start in the beginning? Or go over what?
I've actually been taking notes because I'm a good student.
Oh, okay. So are you kidding me or are you serious? Because I will go over it again if you tell me what to go over again.
No, I do not want to go
Oh,
over
okay,
this
okay,
again.
okay. All right, so oxidative phosphorylation is just a fancy word for sticking a loose phosphate onto ADP to make ATP. Okay, so loose PI, which is a fancy word for a phosphate ion, inorganic phosphate, attached to ADP to form ATP. This happens at a molecule called ATP synthase, which we'll talk about more later. So at the end of the electron transport chain, there's a molecule called ATP synthase, which makes ATP from ADP. And it does it by just grabbing a loose phosphate from the solution, from the water that's surrounding it, and it sticks it onto the ADP to make ATP and gives it high energy. All right. That's oxidative phosphorylation. Why? Because it takes oxygen to do that. Without oxygen, it wouldn't be able to do that. And that's what that is. There's another way to make ATP, though. This isn't the only way. This is the main way, and most ATP is made this way. But a little bit of ATP, they come from, originally they come from your diet. They come from food that you eat. There's phosphates in, there's phosphorus and stuff like that in food. So that's where originally it comes from. But your body has phosphates that are in circulation all the time, that are being used and recycled all the time, like the phosphates that are in DNA, the phosphates in phospholipids, the phosphates in ATP and ADP and stuff like that. Those phosphates can travel from one molecule to another. And remember when we talked about kinases? Those kinases grab phosphates and then stick them onto, another molecule. Now, granted, kinases do it from ATP. They grab the phosphate off of ATP. But anyway, so there's phosphates floating around in the solution all the time. When they're needed, they can get grabbed by enzymes and stuck to a molecule, or they can be released from a molecule to, to float. And then they keep getting used and reused. But originally, you got them from your food. That's where they came from. Hope that answers the question. If not, then just type something else. Okay, substrate level phosphorylation is when a phosphate is stuck to a molecule and then transferred to another molecule, like ADP, for example. So let's say we have a phosphate stuck to this molecule. molecule 1. That phosphate then gets transferred to ADP to form ATP. Okay, so the phosphate was not loose. It was already bound to another molecule, and then it got stuck to ADP to form ATP. And where does this happen? Well, this happens in glycolysis. This happens in the Krebs cycle, but it does not happen in the electron transport chain. That's where oxidative phosphorylation takes place, where the loose phosphates are grabbed. And most ATP is made this way. Most is made this way. Some is made this way in glycolysis and in the in the Krebs cycle. You already know from freshman year that glycolysis can make a couple of ATPs, not a lot, just a little bit. And you know the Krebs cycle makes a little bit of ATP during one of the steps. That's called substrate level phosphorylation. All right, good to go? We good? Shout a question if you have one, or ask me to go over. Anybody except Noah and Sim can ask me questions. All right. I haven't asked you to turn on your cameras. So can you turn your cameras on? Just makes it nicer for me to be able to see if people are with me. I usually do ask you that in the beginning. I just kind of forgot today. So if you could turn them on, that'd be lovely. All right. And if it wouldn't kill you, if it doesn't bring you great, anxiety, if you could keep it on, that'd be great. Can you, okay, hold on. Can you go over the definition again for substrate level? Yes. It's when a phosphate wasn't floating freely, but it was actually stuck to another molecule, and then it gets transferred onto ATP. So if the phosphate that goes onto ADP to make ATP comes from another molecule, then it's substrate level. And that happens in glycolysis, and it happens in Krebs cycle. All right, so what's the other one? What do you mean by writing most and some by the OP? And most means most ATP is made through OP, oxidative. Almost all the ATP we use is made from ATP synthase in the electron transport chain. Just a tiny little bit of ATP is made by those other processes. No, we're specifically talking about ADP going to ATP in this case. So we're talking about specifically making ATP, but there are situations where phosphates are transferred to other things. We just don't call it this then. SLP only in glycolysis and Krebs cycle? Yes. Glycolysis and Krebs cycle. That's correct. ETC is all OP. All right, and we're going to actually touch on this again, so it's going to become more clear as we learn more other stuff, and then we come back to this again. What's fire made of? What's love made out of? Okay, so I got you on that one. Maybe they're made out of the same thing because they both hurt. No, fire is just... No, I'm going to ignore you. I'm sorry. Fire is not a substance. It's just an emission of light and heat from a chemical reaction. So it's not actually a substance or like atoms or anything. Is water wet? Yeah, whatever. All right, let's talk about glycolysis. So glycolysis is basically the splitting of glucose, which is 6 carbons. All right, so we got 6 carbons here into 2 times 3 carbon pyruvates. So pyruvate is only 3 carbons, glucose is 6. And then we split it into 2 3-carbon molecules, which are then called pyruvate. And pyruvate is just a smaller sugar. It's a smaller kind of sugar. It's a triose instead of a hexose, And then that can feed into other mechanisms like the Krebs cycle, for example, to then yield some more energy. All right, so we get a little bit of ATP from glycolysis, not a lot. As a matter of fact, we actually have to pay a little bit of ATP in glycolysis. Before we look at that, let's do this. Glucose to 2 pyruvates. We'll do the freshman version of glycolysis first, then we'll do the AP version, which is this one, okay? So the freshman version is this. We put 2 ATP in. but we get 4 ATP out, which means we make a net profit of 2 ATP, but we also get 2 NADH. Oops, hold on. I wish Microsoft would let me use the undo during the present. I don't know why they don't. I should complain to Bill Gates. So we also get 2 NADHs out. So that's actually kind of useful too. But in terms of ATP, the only thing we get is a net profit of 2 ATP. So we have to pay 2, but we get 4. So that's pretty good. That's a pretty good deal. But really, it's only a 2 net profit. So that's not really very much. Not really very much. So we can divvy up glycolysis into 2 parts. One is the payment, the investment, and then the second part is the payout. So I call it cost, or you could call it the investment maybe. And then the payout part. So let's take a look at that. All right, so basically glycolysis is pretty complicated, but we're only going to look at like half of it in great detail. And then the other half, I'm going to give you a break because if you take biochem in college, they're going to tell you all of these steps too. We're going to kind of just break those down into something a little bit more simple. But for the first part, I'm going to give you all the details. I'm going to give you everything. NaOH, yeah, okay. Okay, so we start with glucose, and this is glucose that you ate. This could be from starch or just plain sugar that you ate or whatever, that then gets transported in your bloodstream and goes into your cells. It's imported into your cells through the membrane, through the glucose shuttle, you know, the glucose transporter protein. And then glucose in the cytoplasm is grabbed by an enzyme called hexokinase. And hexokinase transforms the glucose and adds a phosphate. So kinase, we already know, adds phosphate, and it does that with an ATP. And this is the part where people get confused, and they're like, wait a minute, why are we paying ATP to break this down? We want to get ATP. And yeah, well, that's the investment. We get more out later, so it pays off later. But we have to pay a little bit to play, basically is what it is. So it costs us 1 ATP here. So hexokinase, the hexo just stands for 6. It's a hexose, so it's a 6-carbon sugar, that's glucose, and we attach 1 phosphate to it. It's going to be on carbon 6. That's why it's called glucose 6-phosphate, G6P. All right. Then an enzyme called phosphoglucoisomerase transforms it into fructose. Now you remember glucose looked like this. Okay, so we're sticking a phosphate onto here. Now it's glucose 6-phosphate, and then we're going to transform that into just this, into fructose, which remember was like a pentagon, and then it had this, you know, the 2 extra carbons sticking out from it. So that's going to be glucose 6-phosphate, and this is fructose 6-phosphate. I don't need you to know the structures. I just want you to remember that you actually already know this from biochem. You know what fructose is. You know what glucose is. We're just sticking a phosphate on it. That's all. And because we're doing isomerase here, we're doing an isomer action, we don't need ATP for this because we're just changing the formula. We're not attaching another phosphate. It's still only 1 phosphate here, so there's no ATP here. Okay, and isomerase just means it's creating an isomer. Same chemical formula, different structure. I'm pulling off my arm here, and I'm sticking it on my head. I got all my parts, I still have 2 arms, it's just now in a different place. And that's what it did here. It pulled off that 1 carbon, stuck it in a different place, and it's still a hexose with a phosphate stuck to it. Okay, here's another enzyme called phosphofructokinase. Once again, a kinase, so it's going to require ATP, so that makes sense. It's going to stick another phosphate onto this carbon right here. So here's carbon 1, we're going to stick a phosphate onto here. So now we have fructose 1,6-bisphosphate. Bis means 2 phosphates, 1,6, there's 1 on carbon 1, and there's 1 on carbon 6. All right, and so it's fructose 1,6-bisphosphate. There's 2 phosphates stuck on there. Well, that cost another ATP. We have now paid 2 ATPs in. We have paid 2 ATPs in, so we're in the hole now. We paid money essentially to get this going. Let's hope the investment yields some profits. Here's where things get a little bit complicated, but it's not so bad. Aldolase is an enzyme that's going to split this in 2. This is an aldose. That's just the type of sugar that it is. It's either aldehyde or ketone. Don't worry about that. That's chemistry, biochemistry, babble. Who cares? We don't care about that. But aldolase splits it in two now, and it's going to form one dihydroxyacetone phosphate. So that's 3 carbons. And it's going to form one glyceraldehyde 3-phosphate. So that's 3 carbons. It splits those in 2. Only this one, G3P, is useful. This one is not useful. We don't want this one. So another enzyme called triose phosphate isomerase is going to convert dihydroxyacetone phosphate into G3P, into glyceraldehyde 3-phosphate. This is the useful one. So eventually we're going to have 2 G3Ps because one of them that formed, that made DHAP is going to get transformed by this isomerase into G3P. And the other one was already G3P when it was first formed. So eventually it's going to be 2 of these, which is nice. That's what we need. All right, that's all sounding pretty complicated and everything, but that's because it's just fancy words. And you know something, because it's COVID and we're all, sad and, everybody's crying on the inside and stuff like that. I'm probably okay with you just memorizing these, but it would be nice if you knew the whole thing. Like on the last test, I had kids like write out, the inositol trisphosphate and stuff like that. And some kids got 11 out of 10 on that because they wrote everything out and they had a perfect answer. So I gave them 11 out of 10. Some, not a lot of kids did that, but so if you know IP3, that's cool. But if you know inositol trisphosphate, that's even better. So if you want to memorize dihydroxyacetone phosphate, that's cool. But maybe you don't have to get a good score. Does that make sense? You might say, well, why do we even have to memorize this at all? Because we can just cheat and use notes. Well, I let you use notes last time and not everybody got A's. I mean, I don't know, guys. I don't know what to do here. Like, come on. But I'll tell you this, if we were in person, everybody would have to memorize this. Like no notes. And everybody does. Well, almost everybody. Almost everybody. So you guys are getting off easy, actually. So be happy. You're getting off easier than if we were here, because I would totally make you memorize it. Anyway, okay. So now we're at glyceraldehyde 3-phosphate. That's a 3-carbon sugar. We now got to break this down or not break this down, but convert it to pyruvate, because we're trying to get to pyruvate. That's the thing that we need for the Krebs cycle. This is our goal right here. Okay, so there's 5 steps to do that. 1, 2, 3, 4, 5. We're not going to memorize the 5 steps. Forget about it. I don't even have it memorized. So if I was going to make you do it, I would have to do it, and I'm too lazy. I don't want to. I just have this memorized. So from glyceraldehyde 3-phosphate in those 5 steps, in the first step, we get our 2 NADHs. Okay, good. That's going to be useful later. I told you that's like a coupon for ATP. 2 NADHs. Cool. That's nice. And we get 2 ATP. And we get 2 more ATP. So now over here, we're going to get 4 ATP. Up here, we had -2 ATP. So if you got -2 ATP plus 4 ATP gives you a grand net profit of 2 ATP total from glycolysis. And those NADHs, don't forget, those are nice too. We get those. So, anywho, that's the spiel with glycolysis. That's the spiel. Tonight, after school, when you're sitting around and you don't know what to do, you're waiting to get into your Among Us server, your loading time or whatever, get a sheet of paper out, get a pencil out, and while you're loading, or no, after you got booted from Among Us because they all voted you out because you're ugly, and then write down glycolysis. Wait, did I just say that out loud? I meant to think that part. Oops. Anyway, do you guys play that game or no? Is that only the little kids that play that? No one plays that? Oh.
I play it with a group chat of mine, but that's very rarely, and I have to snatch my sister's phone for it because mine doesn't like it.
Ah. I don't actually have Among Us. I don't even know how to play it. I just watched it on YouTube. All right, let's do a thing here. Let's do a thing, shall we? So I don't know if I'm going to be able to fit it all on here. So maybe what I'll do is I'll probably do the first half on the one slide and then do the second half on the next slide. All right, and I'm going to draw it in, not present mode because it's a lot more user friendly. So if you don't like it, sue me. So it's just going to be a little bit smaller for you. All right, let's start with glucose. Glucose is going to get phosphorylated by hexokinase. This is going to be messier than what I'm doing, than the other one, because it's me writing and it's going to be messy, but and I don't have a lot of space. Hexokinase is going to require ATP because you guys already know that kinases need ATP to stick a phosphate onto something. Well, if I start with glucose and I stick a phosphate onto it, I'm going to get glucose 6-phosphate. Okay? Glucose 6-phosphate. It's spelled out for you on the other page, so I don't have to write it out for you, do I? All right. Then I got to isomerase this into fructose. So I'm going to use phosphoglucoisomerase to switch it over. And that's going to make fructose 6-phosphate. Do I need an ATP for that? Do I need an ATP to isomerase it? Did I add a phosphate? This has one phosphate. This has one phosphate. I didn't add a phosphate, so I don't need ATP. So I'm going to skip the ATP part here. That doesn't have that. Now I'm going to make that bisphosphate thing. So I'm going to need another ATP for this. Because I'm going to stick another ATP on. It's going to be another kinase. That's another phosphate here. This is the most famous of the enzymes. And if you're only going to memorize one enzyme from glycolysis, I'd like you to memorize this one. This one's going to be important later when we talk about regulation of glycolysis. Phosphofructokinase. That's the most well-studied one of glycolysis, and that is one that it is reasonable for me to ask you to know. Phosphofructokinase. It's spelled out for you up here. Okay? So here, this is an important one. Maybe star it, highlight it, whatever. All right, so that's going to make fructose 1,6-bisphosphate. Why is it bis and not di? Because the two phosphates are not
Connected together.
stuck together. They're on different places. One of them is on carbon 6. The other one is on carbon 1. I'm trying to show my hands here, like one up, one down, you know, like, okay, whatever. It's hard to go on the camera with my hands. Okay, anyway, so that's why it's bis. All right, that's good. Oh, maybe I do have room to fit all this on one slide here. Okay, so then I'm going to use aldolase to split this. Aldolase is going to split it. It's going to make dihydroxyacetone phosphate over here, which is useless. We can't use that for anything, so we have to convert it to glyceraldehyde 3-phosphate, which is useful. All right, and the way with it, so this is aldolase. And then, so the dihydroxyacetone phosphate gets converted to glyceraldehyde 3-phosphate by triose phosphate isomerase. You might say, why is your arrow going to the left and to the right? Because this can go either way. It can take glyceraldehyde 3-phosphate and switch it to dihydroxyacetone phosphate. Or it can take dihydroxyacetone phosphate and switch it over to glyceraldehyde 3-phosphate. It doesn't give a rip. It goes either direction. It does not give a rat's behind which way it goes. However, the overall reaction will go into this direction mainly. Why? Why is it mainly this direction and hardly this direction?
Because nothing happens on the left.
True, this doesn't go anywhere. Like this can't go anywhere. This is stuck. But what happens to this? What happens to G3P? Does it stay G3P or does it get changed and removed? What happens to G3P? Does it just stay there stagnant? It's stuck there, or does it get, are there more arrows below it?
It gets
There's
converted
more
to
arrows.
phosphate.
There's more arrows, which means it's going to get converted and it's going to get used up. It's going to get taken away. Well, if this gets taken away, then this enzyme is mostly going to be grabbing these. almost any time it grabs something in that solution there, it's going to grab dihydroxyacetone phosphate, which means it's going to go to the right. Because it's hardly ever going to grab one of these, because these just get taken away by these other enzymes here. So that's why overall, the direction of this reaction is to the right. Oh, my arrow looks really good. It looks like a werewolf arrow. Look at that. It's transforming. Okay, we got 5 arrows here. 1, 2, 3, 4, 5. Oh, I just fit it on. It just fit it on. Okay, in the first one, we get NADH. But this is times 2, so we get 2 NADH. Because there's 2 of them now, one from this, one from this. In the second one, we get ATP. But we get 2 ATP because we do it twice. In the 5th one, we get ATP. But we get 2 ATP because we do it twice, because we have 2 of these forming from 1 fructose 1,6-bisphosphate. How is that possible? Because fructose 1,6-bisphosphate is 6 carbons. This is only 3 carbons. We split it in 2 to make the dihydroxyacetone phosphate and the glyceraldehyde 3-phosphate. Each of these is only 3. That's why we get 2 of them. That's why everything is times 2 here. I think the more I circle crap, the worse the drawing gets. So I got to stop doing that. I'm just kind of addicted to like drawing arrows on top of arrows and circles on top of circles like these here. Like if I circle this 5 more times, I think you'll learn it better. Like, look at this, like, oh my God, it's so much clearer now. Yeah. Way to go, Volk. What stimulates glycolysis? Okay, nothing stimulates it. It's just kind of like always happening. It's always going on. It never really stops. However, we can slow it down and we can maybe sometimes stop it if there's too much ATP in the cell. So if there's too much ATP already, like the cell has everything it needs, it's just very temporarily stops it at phosphofructokinase. This enzyme gets shut off here, and then all of it kind of stops. Okay. When you ask these questions, put them in global chat so everybody can read them. Then people know what I'm saying. What else did this add? Okay, so it doesn't give both. It either becomes DHAP or G3P. No, it's going to do both. It cannot make 2 of one, so it makes 1 of each, and then the DHAP has to get transformed by the other enzyme to make G3P. So what's the point of even? Oh, that's the only thing it can make. Like if you split that large molecule, it automatically forms 1 of the DHAP and 1 G3P, because they're slightly different on each end. The structure is slightly different. It's not a perfectly symmetrical molecule. Does that make sense? So one is slightly different. So that it's not like it does it on purpose to make the wrong one. That's the only way it can do it. And then it has to be changed because it's the wrong one. So I hope that answers the question. If you guys can put those questions into the global chat, then yep. DHAP doesn't really have a purpose at all. It's just like accidentally was made the wrong one and it has to get transformed into the other one that's the right one. That's exactly right. So thank you for asking that. Okay. Oh, by the way, I didn't put the end product down here. Like I didn't have space for it. So maybe I can write it in the no man's land here. Oh, hold on. Let's see if this works. Can I go into no man's land? Oh yeah. So I can do 2 pyruvates down here. It's going to be off the slide. Pyruvates. Oh my God, Volk. All right, so pyruvates are the goal. That's what we got now. Do you remember the days where the mitochondria was the powerhouse of the cell? Those were the good old days. When that's all we had to know in 8th grade or 7th grade, oh, that was nice. Back then we didn't appreciate it, you know. We took things for granted, but man, to have those days back. And now it's all about dihydroxyacetone phosphate and glyceraldehyde 3-phosphate and, you know, chlorophyll more like borophyll. Oh my God. Well, that's coming up in the next chapter. Borophyll is all in chapter 10. So yep. May I move on? I was having thoughts in my brain, like what are the odds that I can get through the whole chapter in one class? Well, right now I'm looking at the time. I only have 17 minutes left. It's not looking real good because this does not end at 2:30. It ends at 1. Yeah, but anyway, I still would like to get through the Krebs cycle if I might. Please. Nevada, you all right? She's capitulating over there. Oh my God. Anyway. Okay, citric acid cycle. Fine. Gonna be all trendy just because our textbook calls it that and all these college professors. I'm old fashioned. Not that either. T-Pog. Okay, who remembers Pukey, a clown, and all that? Pukey. Yay. T-Pog. I don't know what that means. Okay, whatever. Moving on. Oh, I'm going to use this slide here to give you like an overview of what the heck is even going on. So let's check that out. What is even happening here? Okay, swap presenter view. Go to this. Go to that. A little bit of this. Okay, so basically the deal is this. If we're going to look at big picture. Big picture is this. Here's the cell, right? Glucose comes in from the blood, goes into the cell. The capillary brings the glucose from your food, from your, small intestines, got absorbed there into the bloodstream, brings it over, goes into the cell, and then glucose gets broken down in glycolysis in the cytoplasm. All right, over here you got a mitochondrion. All right, so this is a mitochondrion. What's happening in glycolysis is the glucose gets changed into 2 pyruvates. All right, so then pyruvate gets imported into the mitochondrion. So now you got pyruvate in there. So now the pyruvate enters the Krebs cycle. And the Krebs cycle makes a whole bunch of NADH and other stuff, but mostly NADH is the main thing. Okay? Let me fix that a little bit. I thought I'd have a little more space here, but I'm a bit low on space. So let me try to write it smaller. Here we got the Krebs cycle. So the Krebs cycle takes the pyruvate and produces a whole bunch of NADH. So now a lot of that energy from the pyruvate and from the glucose is in the NADH. A little bit of it is lost as heat, and that's why we got like body heat and stuff like that. I mean, there is heat produced. So that's why we have a, 97, 98.6 or whatever the body temperature from that heat, okay? So that NADH then goes to the inner membrane of the mitochondrion, goes right there where those cristae are and like here and all that stuff. And that's where then we have the ETC happening, and that makes a whole lot of ATP. So that's the relationship that we got going on here is we got glycolysis first in the cytoplasm, then go into the Krebs cycle, then the energy goes to the electron transport chain, and that's where we make our ATP. That's where most of the ATP is made. So another way we could make this diagram is like this. We could do this. We could say glycolysis, Krebs cycle, and then electron transport chain. All right, so that's like the relationship. Well, what do we have going from glycolysis to the Krebs cycle? Well, it's pyruvate. What do we have from the Krebs cycle going to the electron transport chain? Well, it's NADH. mostly. There's other stuff too, which we'll learn about or whatever. And then the NADH takes that energy. And then what do we have coming out of the electron transport chain? Well, we have ATP. And, you know, if you wanted to, you could add like food up here. You eat food. That feeds in, that glucose then feeds into glycolysis, and that's the spiel. The electron transport chain happens to need oxygen. It needs oxygen gas to make this happen. Without oxygen, this is not going to happen. It's going to die. It's going to slow down. It's going to stop. So this is why we need to breathe oxygen for this to work. That's why we're breathing. That's the only reason we need oxygen. This is why we eat food, is for this to happen. Is that a good overview, or is that too confusing? Is that like a big picture overview? Just kind of not a lot of detail? So if you stopped eating, then you wouldn't need to breathe. Yeah, okay, yeah, sure. Okay, you give that a try. See how that goes. Just hold your breath for like 15 minutes and then report back to us, okay? Well, we can put more detail into this, but we can keep it big picture. And the College Board for like the AP test, this is what they want you to know. They don't want you to know all the detailed steps. They don't need you to know dihydroxyacetone phosphate. That's okay. You just need that from me. Why am I making you learn it? Because I'm out of my mind. Okay, but the College Board for the AP test, you don't need to have it all memorized. So in May, when you're studying for the test, or you're going to be studying for the test before May, but in May, when you take the test, you don't need to go in there all anxious, like, oh my God, I got to have all this memorized. No, you don't. You just need to know the big picture. Okay, and I'll give you a more detailed big picture at the end of this, the one that I want you to, take home from this. You know, when the class is over, I want you to, that's the big picture I want you to keep. Can class be over early? Hell no, I was thinking about going late so we can get more done. So we only breathe for the ETC, that's exactly right. The only reason we breathe oxygen in is for the ETC. Well, we also need to remove CO2. So the Krebs cycle then, so here's some more details in the big picture. The Krebs cycle releases CO2. And that's why we have CO2 in our breath breathing out. It's from the Krebs cycle. Where does that CO2 come from? Well, it's from these pyruvates. There's 3 carbons here, remember? Those 3 carbons are going to make 3 CO2s. All right? Because 3 carbons here, each of them is going to make a CO2. Each CO2 has 1 carbon in it. And that's where the carbon goes. So anyway, you can't schedule work when you have class scheduled. School comes before work. So don't tell me you got a job during my class. Come on. Come on. People, killing me. If anybody, I mean, if you have to leave class for an emergency for something, obviously I'm going to allow you to leave. I can't stop you. Like I'm going to hold on to you. What am I going to do? Like I can remote lock your door or something so you can't leave. I should get a button like that so I can like lock you in your room or something. You can mark me absent. Yeah, maybe I will. Now that you made a big deal about it. And nobody knows who I'm even talking to because it's all on private chat. I will not reveal the guilty. I will not reveal. It's going to be a big secret who it's going to be. All right. Krebs cycle today. I promised you the Krebs cycle. We will talk about the Krebs cycle. All right. So the Krebs cycle that I just talked about in the big picture is shown here for us. Let's check it out. The way you're going to memorize this is with the mnemonic. The mnemonic is Pukey a clown. Check it out. Pukey a clown is at South Carolina State Fair making orange juice. No, not orange juice, origami. Orange juice is my old one. Origami is my new one. All right. Omelets. If you want to go with omelets, you may, but anyway, making origami. Okay. Pukey a clown is at South Carolina State Fair making origami. The person that was talking to me about having to leave to go to work, go ahead, but don't make this an everyday kind of thing. You can go ahead and go to work, but you know the Krebs cycle already. You had me for honors. You have all those. It's the same Krebs cycle.
Volk, I meant, can we like end early so we can go to TSS? Because I have to, do that test thing.
Oh, yeah. We can, TSS doesn't start till 10 minutes after class.
I know. I don't start until 4, but I'm not trying to be in here till 1:30 with you looking at the Krebs cycle.
Now everybody knows who it was.
I don't care.
Okay, so we know how to memorize the steps. We know how to memorize the compounds with Pukey. That's easy. But how are we going to memorize where NADH forms? Well, the way we're going to memorize that is with this little cheat code. We're going to say yes, no, no, yes, yes, no, 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 yes. That's my cheat code. 1 yes, 2 no's, 2 yeses, 3 no's, 1 yes. So we look at the steps, the arrows. Those are my yeses and no's. Here's the first arrow. Yes, we make NADH. No, no, yes, yes. Are you with me here? That's my yes, yes right here. No, 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 yes. Bam. That's how we remember where NADH comes out. That's actually not that hard. It's easy to remember 1, 2, 2, 3, 1. It's easy to remember that sequence of numbers. 1, 2, 2, 3, 1. Pretty easy. Sim, you better have a good reason if you're going to leave. As a matter of fact, if you want to test me, I'll find a way to make you stay after. Okay. Anyway, everybody good on the NADHs? That's when the NADHs form. Okay, so per pyruvate, how many NADHs are we making? We're making 1, 2, 3, 4 NADHs per pyruvate. So if somebody asks you like on a test or whatever, how many NADH per glucose? You're like, oh, 4. No, wrong, Timmy. How many pyruvates do I get per glucose?
8.
Okay, let's start again. How many pyruvates do I get per glucose?
2.
2. 2 times 4 is, now say the other thing.
8.
8, exactly. So it's 8 NADH per glucose. So that's pretty sweet because we can get a lot of ATP from those NADHs. As a matter of fact, we're going to get about 3 ATPs per NADH. Pretty good. All right, moving along. The other thing we get is FADH2. So I haven't mentioned that yet. FADH2 is kind of like NADH, but it's not as good. You know, it's like my kids at home, I got my favorite, that's NADH, and then I got my like less favorite one, that's FADH2. It's like the lesser child. All right. FADH2 can only get us 2 ATPs. It's not quite as, you know, hardworking as NADH. And we only get 1 per pyruvate. So maybe that's all right because we get a lot of NADH. We only get 1 FADH2. It comes right before fumarate. Before fumarate. So it's easy to remember F and F. FADH2 before fumarate. Easy. And then we got ATP. Well, it says GTP here. In some cells it's GTP. In some cells it's ATP. So let's call it ATP. ATP is sassy because it's full of energy and it's sassy. It's between succinate and succinyl-CoA. All right, so ATP forms between succinyl-CoA and succinate, SAS. So that's how you're going to remember ATP. That's easy. Yeah. Hampel, you know what I'm talking about, the lesser child? Yeah. You know exactly what I mean. That was always me, my family. Anyway. All right, so how do we pronounce these? Pyruvate, acetyl-CoA, citrate, isocitrate. And by the way, this is why it's called the citric acid cycle, because of citric acid. Citrate, citric acid, the same thing. Isocitrate, alpha-ketoglutarate, you can make the alpha like this. Succinyl-CoA, succinate, fumarate, malate, oxaloacetate. All right, when we have in person, I make the kids memorize this. So I'm going to ask you to memorize it. I'm going to ask you to memorize it. Well, you're going to know that we're not cheating to you. Well, I don't, but memorize it anyway, because then on a test, you can get through the questions faster. I might not even make you draw this out on a test. I might just ask you about it. What'll happen if I cut this off, or what happens if this is inhibited, or whatever, you know? So knowing it, having it memorized might help. But I might give you a quiz next week. Maybe a quiz, closed note quiz. So we'll figure that out. All right, how are you going to memorize this? How are you going to learn it? By drawing it out. You will not learn it by staring at it. You will learn it by drawing it out, writing it out in a big circle, doing the Pukia clown, doing the yes, no, no, yes, yes, no, 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 yes, doing the SAS, doing the before fumarate, FADH2. Everybody clear? It'll give you something to do this weekend. Draw these things out. And then your mom's like, oh, what are you doing? Like, hey, check it out, Mom, it's the Krebs cycle. And Mom looked at me like, oh my God, that's so impressive. Like, oh, wow, you're so smart. Let's go to Culver's. Like, seriously, moms do that all the time. Right, Abigail? All the time they do this. Right? So basically then you're going to get Culver's because of my class. What a good deal. Amount of NADH produced in the Krebs cycle is my relationship with this class. 4. You're getting a 4 in my class. That's a good score. Check it out, Mom. I'm not a disappointment. Yes, exactly. My mom would call me a nerd. That's nice. Yes, no, yes, yes, no, 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 no. Yes, I didn't get anything when I did that last year. What? You got ripped off. Then she owes you 2 times Culver's. 2 Culver's. 2 kids' meals in one trip. I feel confident about this test during TSS. And then it just says Amira. Okay. Are we done? It's 1 o'clock. Yeah, I don't know what any of that means. I'm going to shut it down. I'm going to start the TSS Zoom. If you need to talk to me about the test or about any questions from today's class, please stop in. Otherwise, have a great weekend. Memorize glycolysis, memorize Krebs cycle. See you.